Okay, now let's do some examples, or go through some examples kind of in depth, step by step, on showing how to calculate eigenvalues and eigenvectors for a given matrix. Let's quickly remember what the procedure is here, right? Well, we know that eigenvalues and eigenvectors satisfy the equation AX equals lambda X, where A is an n by n matrix. Lambda is a complex scalar, right? I mean, when I say complex, you'll note that the real numbers are a subspace of the complex numbers. And so when I say complex, what I mean is possibly complex, right? So like when I say for these lambdas such that the determinant of lambda I minus A is 0, and when I say when these are in C, right? If I write for C, let's get rid of for all there. What I mean is possibly complex, right? And so really, real numbers are complex numbers also, whose imaginary part is 0. But anyway, so we're looking for a scalar lambda and vector x such that AX equals lambda x. How do we do this, right? The first step is going to be we solve the characteristic equation or find roots of the characteristic polynomial. Once we do that, we found the eigenvalues. And then we take the eigenvalues, we plug them in to this equation, lambda I minus A times x equals 0, and solve for eigenvectors, right? That'll get us the eigenvectors. So what I want to do is I want to do a 2 by 2 example and then a 3 by 3 example. So let's start with the matrix. So let's say we want to find eigenvalues and vectors for A, which is given by -5, 2, -7, 4. Okay, what was the first step of our procedure? The first step of our procedure is to set up the characteristic equation. i.e. the determinant of lambda I minus A is equal to 0. So let's just compute the characteristic polynomial first, and then we can set it equal to 0, right? So what's lambda I minus A? Well, A is 2 by 2, so that means I is going to be the 2 by 2 identity matrix. This is equal to lambda times I2 minus A, so -5, 2, -7, 4. We can simplify this a little bit to become lambda 0, 0, lambda, right? That's scaling the identity by lambda. And then minus A, -5, 2, -7, 4, which looks like lambda I minus A is going to be, well, what do we have, right? We have lambda minus a -5, so lambda plus 5. And then we have 0 minus 2, so -2. And then we have 0 minus -7, so +7. And then, right, that's just based on this equation here. And then I have lambda minus 4. So here is lambda I minus A. And now we want the determinant of this matrix. So we're taking the determinant of lambda plus 5, -2, 7, lambda minus 4, which is lambda plus 5 times lambda minus 4, and then minus -2 times 7, which looks like we're going to get lambda squared plus 5 lambda minus 4 lambda minus 20 plus 14, which means our characteristic polynomial is lambda squared plus lambda minus 6. This is our characteristic polynomial. Now, to find the eigenvalues, we find the roots of the characteristic polynomial, which means we set up the characteristic equation, right? i.e., we solve lambda squared minus 6 lambda, or what am I doing? How about lambda squared plus lambda minus 6 equals 0? Well, this factors nicely, which will not always be the case. So this factors to lambda plus 3 times lambda minus 2 equals 0, which means we have two solutions here. We have lambda 1 equals -3 and lambda 2 equals 2. These are the eigenvalues for the matrix A, which was -5, 2, -7, 4. Awesome. So we found the eigenvalues. Now that's completed step 1 of our procedure here, right? We found eigenvalues by solving the determinant of lambda I minus A equals 0. And now we need to find the basic eigenvectors for each eigenvalue. So let's start here. This is going to be step 2 now of our procedure. And let's say step 2, part A, because what we're doing is we're looking first at just, right? We need to do step 2 for each eigenvalue. So let's start with lambda 1. Lambda 1 equals -3, right? Then what are we solving? Now we're solving, we want to find x1 such that lambda I minus A times x1, and this should be lambda sub 1I, right? Lambda 1I minus A times x1 equals 0. That means we're looking for -3I minus A times x1 equals 0. And really this -3I minus A, well, what you do is you just come back to what lambda I minus A is. And now we plug in lambda equals -3, right? So we'll have -3 plus 5 is -2 for the first entry, right? So -3 plus 5, that's -2. And then we had -2, 7, and then lambda is -3. So we have, well, sorry, we have -3 plus 5, which is +2, right? Let's look at what our, let's slow down here and look. We have -3 plus 5, which means that's +2. And then we have -2, 7, and then -3 minus 4 is -7. Okay. Times, and then let's say x1 is equal to x1, x2, right? Then we're looking for the vector x1, x2 such that this is equal to 0, 0. i.e. the eigenvector here is just the solution to the system 2, -2, 7, -7, 0, 0. Right? If we find the solution to this system, then we found the eigenvector for the eigenvalue lambda 1 equals -3. So you'll notice here, row 2 is a multiple of row 1. If you were to take row 2 times 2 over 7, row 2, right? If we did row 2 is being switched with 2/7 row 2, then you would have 2, -2, 0, and then 2, -2, 0. Then you take row 1, or how about row 2 is row 2 minus row 1. And then let's also, the new row 1, so row 1 new, well, it's the same because we're only changing row 2. Like, let's say row 1 is 1/2 row 1, then that gives us 1, -1, 0, 0, 0, 1. This is the reduced row echelon form, right? This means, this implies the row of all zeros at the bottom implies we have a free variable. So this gives us x1. Well, really, it tells us x1 minus x2 equals 0. So x1 equals x2. And then we have at the bottom here, x2 equals t for t and r. So what does this mean? This means our eigenvectors, our x1 is t, t. And not to be confused here, this is the capital X1. right? I'm also using, which may be a little inconvenient, I'm using this lowercase x1 to denote like the first component of the vector big X1, right? So just to avoid ambiguity here, this is capital X1 equals TT, which is T times 1, 1. And so our basic eigenvectors, or our basic eigenvector we could look at is X1 is 1, 1. And this was for lambda 1 equals -3. Great, so we found the eigenvector, or the basic eigenvector corresponding to the first eigenvalue. Now let's do procedure part 2, part B, right? Which is we need to do the same thing now for lambda equals, I believe the second eigenvector was, or the eigenvalue was +2, right? Let me double check here. Drawing a blank on what we got. Correct, it is +2. So let's do the same procedure now for lambda 2 equals 2. So lambda 2 equals 2. We need to find x2 such that lambda 2I minus a times x2 equals 0, right? And then lambda 2I minus a, well, again, we just come back to the formula we found for lambda I minus a, but now we plug in lambda 2 equals 2. And so that looks like we're going to get a 7 in the first spot, and then -2 in the, or in the A11 spot, and then in the A22 spot, we'll get -2. Right? This is then the matrix 7, -2, 7, -2 times, now lowercase x1. I'll try to make these more squiggly so you understand that it's lowercase. X1, x2 equals 0, 0, right? Now we're solving for the vectors x1, x2. Well, you'll notice row 1 and row 2 are the same. So if I did row 1, or row 2 equals row 1 minus row 2, I would get, well, let's set up the following system first, right? We would have 7, 7, -2, -2, 0, 0. Let's just be explicit here. Row 2 is row 1 minus row 2. And then row 1 is, let's do 1/7 row 1. And so that would give us 1, -2/7, 0, 0, 0, 0, right? And so this would imply that x1, again, I'll try to make these more, x1 equals 2/7 x2, and then x2 is, say, s, for s in R, right? That's our parameter. And so what are our eigenvectors in this case? Well, it's going to be 2/7 s and s, which if we take the basic, let's let s be 7, we get the basic eigenvalue or eigenvector x2, capital X2 equals 2, 7, right? And so this would be the eigenvector for the eigenvalue lambda 2 equals 2, right? And so here it would be very important to verify, right? Here's kind of our phantom step, our step 3, verify. And I'll leave the matrix multiplication to you all, and I want you to actually do this to go ahead and verify that these are in fact for the eigenvalues that we computed, these are the basic eigenvectors, right? Okay, so here's an example of how you would find the eigenvalues and eigenvectors of a matrix here. Okay. Excuse me. This is for a 2x2 case. Let's do a 3x3 example. So blah, blah, blah. Let's do a 3x3 example. So let's find the eigenvalues and eigenvectors for A equals the following matrix. It's 3 by 3. So 5, -10, -5. For the first row, 2, 14, 2. For the second row, and then -4, -8, 6 for the third row. Great. What's the first step of our procedure? The first step is to set up and solve the determinant of lambda I minus A equals 0, right? This is always the first step, doesn't matter what dimension you're working in. So what do we have, right? Or i.e., we're trying to set up and solve our characteristic equation. Well, let's compute lambda I minus A. You can notice what this will be. You don't have to write this out every time. Well, the diagonal here, like the AII or AJJ entries here, is just going to be lambda minus the entry of A. So we'll have lambda minus 5, lambda minus 14, lambda minus 6. Right? And then what do we notice for every other entry, right? Well, if you take the identity minus a matrix, every element that is not along the diagonal of the identity is 0. So that means we're going to have 0 for every other entry here. We're going to have 0 minus whatever the corresponding element is in A. And so what that corresponds to is just flipping the sign of every other element. So we have 10, 5, -2, -2, 4, and 8. Like this. And so this is our lambda I minus A. And now to find the eigenvalues, we need to take the determinant of this matrix, set it equal to 0, and solve for lambda. So we want the determinant of lambda I minus A, which is the determinant of lambda minus 5, lambda minus 14. I'm going down the diagonal again here, lambda minus 6. And then we flipped the sign of everything. So 10, 5, -2, -2, 4, and 8. Okay, so let's take the determinant here. How do we take the determinant? Well, to take the determinant of a 3 by 3, we start with the first. I mean, you can pick whatever row or column that you want. When there's not a lot of zeros or no zeros, I always just kind of go across the top here. So you start with the first entry, you block out the row and the column that entry belongs to, right? And then you take that entry times the determinant of the corresponding cofactor, the 2 by 2 there. So we have lambda minus 5, and then that's going to be times lambda minus 14 times lambda minus 6, and then minus a -16, so plus 16. We go to the next element here, right? So that was for lambda minus 5. For 10, we flip the sign, and then minus 10 times, and then we take the corresponding determinant of the cofactor here. So we have the determinant, we'd have -2, let's just write this one out, -2 times lambda minus 6, and then minus a -8, so plus 8, and then we do the same thing for the 5, right? So then we flip the sign again, so plus 5 times, then we're going to have -2 times 8 is -16, and then that's going to be minus 4 times lambda minus 14. Okay. Now we have to simplify all of this. Let's see what the first term simplifies to. The first term simplifies, well, we have a lambda minus 5 factored out front, and then we have lambda minus 14 times lambda minus 6, which is going to give us lambda squared. And then minus 6 lambda minus 14 lambda is minus 20 lambda. And then we have -6 times -14, which is positive 84. And then 84 plus 16 here, this 16 is 100. So that's going to be plus 100. And that was for the first term, right? Let's see how the second term simplifies. Well, we have -10 times And then it looks like we're going to get negative 2 lambda plus 12 plus, so that's going to be 20 minus 2 lambda. And then let's see what we have for the last term. We have negative 16 minus 4 times 14. 4 times 14, well, that's going to be a positive 28 times 2, which would be, well, 28 times 2 would be 56 minus 16 is 40, right? So 40, so that's plus 5, and then 40 minus 4 lambda. Sometimes it's the basic arithmetic that gets you, right? That simplified to 40 minus 4 lambda. But what do we notice here? Right now we've simplified everything. We need to simplify this even more. You may notice that this term here is equal to 2 times 5 times 20 minus 2 lambda, right? Or excuse me, if you multiply the 2, again, basic arithmetic, if you multiply the 2 there, you split that up, that 10 is 2 times 5, and then multiply the 10, you're going to get 40 minus 4 lambda. And so we have a negative 5 plus 5 times 40 minus 4 lambda, which means, luckily, those terms cancel. This simplifies to lambda minus 5 times lambda squared minus 20 lambda plus 100. Cool. Now what do we have, right? Now we're simplifying this. We're solving for, well, right now we're trying to find the characteristic polynomial so that we can find the roots of it, right? Well, we have the lambda minus 5 here. How could we simplify this lambda squared minus 20 lambda plus 100? Well, if you look at multiples of 100, you'll see that you can get positive 100 by negative 10 times negative 10. So it's going to be lambda minus 10 quantity squared. And you have that negative 10 minus negative, or negative 10 plus negative 10 is negative 20. And so our characteristic polynomial is the determinant of lambda I minus a. This simplifies to lambda minus 5 times lambda minus 10 quantity squared, right? Now to find the eigenvalues, we set this equal to 0. So we have lambda minus 5 times lambda minus 10 quantity squared equal to 0, which means we have an eigenvalue of 5, and then we have 2 eigenvalues of the same value. That corresponds to a double root in the characteristic polynomial. And this is fine. We just say this is an eigenvalue of multiplicity 2, right? So if you have a repeated root in your characteristic polynomial or a repeated solution in your characteristic equation, that's fine, but it's worth noting then that you have an eigenvalue of that given multiplicity, right? And since we have 2 copies of the eigenvalue 10 here, this is an eigenvalue of multiplicity 2. But the process is no different, right? These are our eigenvalues. Okay, and so now that was step 1. And for step 2 is for each eigenvalue, we need to find, so for lambda 1 equals 5, we need to find the basic eigenvector, right? How do we do that? Well, we need to set up lambda 1 I minus a times capital X1 equals 0, right? Well, here lambda I or lambda 1 is 5. So we have 5i minus a times X1 equals 0. Again, we can just go back to what lambda I minus a is, and we plug in 5, right? If we plug in 5, you can see everything except the diagonal is going to stay the same. And then along the diagonal, we'll have 0, -9, -1. So this value, this is along the diagonal, we have 0, -9, -1. Everything else stayed the same. So 10 5, -2, -2, 4, 8 times x1. Again, these are lowercase. x1, x2, x3 equals 0, 0, 0. So the eigenvector x1 is just going to be, or the eigenvectors plural, right? Because we're finding a family of eigenvectors every time. And then our answer just ends up being like the basic one, or one that would constitute like a basis of this subspace. So we need to solve the following system: 0, -2, 4, 10, -9, 8, 5, -2, -1, 0, 0, 0, right? We're always solving a homogeneous system of equations. So in reduced row echelon form, and I'll leave those steps as an exercise, right? Hopefully we're very comfortable at doing this by now. What I got was 1, 0, 0, 0, 1, 0, -5/4, 1/2, 0, 0, 0, 0. And so maybe you should check and make sure I didn't make any mistakes here in my steps. But this was the reduced row echelon form that I got. And what does this mean? Well, this means we have, for the first row, that says x1 minus 5/4 x3 equals 0. The second row says that x2 plus 1/2 x3 equals 0. And then the third row is all zeros. So that tells me that x3 is equal to x3. So if we let x3 be the parameter t and r, well, then what is our family of eigenvectors? That's going to be, well, we have to add that over. So it looks like we're going to get 5/4 t, -1/2 t, t, right? And then to get the basic eigenvector, what we do is we just find an integer solution to this. So let's let t equal 4. If we let t equal 4, then our eigenvector is going to be x1 equals 5, -2, it looks like, and 4. And so this was for the eigenvalue, lambda1 equals 5. So we found the basic eigenvector corresponding to the eigenvalue lambda1 equals 5. We need to do the same thing. And so this is part B and C because we have a repeated root, right? This is for lambda2 equals lambda3 equals 10. So what do? Well, we do the same thing. We set up lambda2. I'll just write lambda2 comma 3 there to indicate that it's both I minus, or it's interchangeable, right? It's not both at once, but it's interchangeable. It's the same process. Minus a times x, and let's just leave this as x on its own, equals 0. Okay, well, what does that mean, right? We go back to, this is 10i minus a times x equals 0. We go back to our calculation of lambda I minus a, we plug in 10, and for the sake of time, let's just see what I got here. Well, it's going to be lambda minus 5 for the first entry, so that's 10 minus 5, which is 5. For the second one, it's going to be 10 minus 14, so -4, and then we'll have 10 minus 6, which is 4, right? Everything else stayed the same. So 10, 5, -2, -2, 4, 8. And this is times, let's just go x, y, z here. Or now let's do x1, x2, x3, x1, x2, x3, right? Since there's no subscript in the capital X and the vector x, there's no ambiguity anymore. So now we're solving for this system, right? Or we're solving for solutions of this system. And to set that system up, we would set up the augmented matrix. 5, -2, 4, 10, -4, 8, 5, -2, 4, 0, 0, 0, right? And again, I would ask you to check me and make sure I made no mistakes in my calculations here. The reduced row echelon form I got is 1, 2, 1, 0, and then I have 2 rows of zeros. So this is the reduced row echelon form I got of the augmented matrix. It will help us find the eigenvectors here. And so what does this mean? Well, this means that x1 plus 2x2 plus x3 equals 0. But then we have that x2 and x3 are both free variables, right? So we have parameters s and t. What does this mean for our eigenvectors x? That means we have the eigenvector 1, well, no, x1, we need to subtract 2x2 over. So that would be -2, but x2 we're saying is s. So -2s minus t and then st, right? Again, for s and t in the reals. We can split this up a little bit. So x, what we just got was -2s minus t, st. You may notice this is -2, or sorry, s times the vector -2, 1, 0 plus t times the vector -1, 0, 1. And so what this means then is really we have, since we have two, we have a eigenvector or an eigenvalue of multiplicity 2, that means we need to find 2 eigenvectors, right? Well, and we've just found them. We just found the basic eigenvectors. Right, and so without loss of generality, let's say x2 is equal to the vector -2, 1, 0, and then x3 is equal to the vector -1, 0, 1. This is for lambda 2 equals 10, and for lambda 3 also equals 10, right? And so this is how we find eigenvectors when an eigenvalue is of multiplicity more than 1, right? It's the same process, but you'll see the result will spit out more than one eigenvector, right? Or more than one basic eigenvector that would define like a basis for this solution space here. Okay, so we've now done a 2x2 example and we've done a 3x3 example. I want to do one more example. You may have noticed, like in this example here, the matrix A we were working with, the numbers were getting into inconvenient territory. These numbers weren't so bad that I couldn't do the arithmetic in my head, or that we couldn't do the arithmetic in our head, but it's on the verge of it, right? Any more complex or any bigger numbers, and then the arithmetic would start to get really annoying and pretty cumbersome, and you'd want to get a calculator out and start verifying all these products of these larger numbers, et cetera, et cetera. There's a way around that in certain cases. So let's see how we can, if a matrix is really kind of messy to work with and calculated determinant and things like that, let's see when we can avoid that. So let's start with a definition here. Let's let A and B, let's let these be 2 n by n matrices. Now, if there exists a matrix P invertible such that A is equal to P inverse times B times P, or P, B, P inverse, either, doesn't matter. We say A and B are similar. So this is a notion of similar matrices. Okay, so if there exists this invertible matrix P such that if you kind of sandwich B or one of the matrices between this invertible matrix and its inverse, then we say these are similar. So these are similar matrices. Okay, now why do we care about similar matrices in the context of calculating eigenvalues and eigenvectors? Well, we care because it's the following theorem. If A and B are similar, this implies that A and B have the same eigenvalues. So this is a pretty important theorem here. It says if you have two similar matrices, they have the same eigenvalues. Now, why does this make our life easier, right? You can say, well, great. How do I find a similar, or how do I find an invertible matrix, right? This is just saying if it exists, then I can use it. But the real question here would be like, well, how do I find an invertible matrix? It would make my life easier. And you can always take P to be an elementary matrix, right? So let's say we have A is some matrix. And let's say that B is a matrix obtained from A by an elementary operation, by one row operation. Right? Well, we know that elementary matrices, so E, an elementary matrix. Remember, what is an elementary matrix? That's a matrix that is one, it's one row operation off of the identity, right? And so if we did a row operation, let's say R, then E sub R, this is the elementary matrix such that, well, then this is basically a matrix representing what you would do, right? Then you would have that A times ER equals B, right? Because, or how about ER times A? Either way, right? And what that's doing is whatever this row operation was, R, when you multiply A by this elementary matrix representing that row operation, then B is just the result of what that row operation would have done, right? And so we can always use these as our invertible matrices. Let's see an example. Let's say we want to find the eigenvalues of A, which is 33, 105, 105, right? And you can already see computing a determinant here would be a nightmare, right? So 10, 28, 30, negative 20, negative 60, and negative 62. Now, how do we use this theorem that says we want to find the eigenvalues of this matrix, right? But we want to use a theorem that says if there's a similar matrix B, a matrix that's similar to A, then they have the same eigenvalues. Well, what do? We can say, basically what we do is say, I want to start to take A and push it to a row echelon form of a matrix, right? What would my first step be there? The first step I would do here is I would take 2 copies of row 2 and add it to row 3, right? You can see that would get me a 0 down there. And that, adding 2 copies of row 2 plus row 3, that is the elementary matrix, like the matrix representing this move. That's the elementary matrix E22, right? And so what that means is I can take A and multiply E22 times A times E22 inverse. And I'm guaranteed that the output is a matrix similar to A, right? And so if I did that, what is this product? Well, what's E22 given by? That's given by 1, 0, 1. No. Right? It's that row operation off of the identity. So that would be 0, 2, 1. right? Like this. So, and then I have times A, which is 33, 105, 105, 10, 28, 30, negative 20, negative 60, negative 62. Elementary matrices are guaranteed to be invertible, right? And so the inverse is easy to calculate here. That's 1, 0, 0, 0, 1, negative 2, 0, 0, 1, right? It's just flipping the sign of whatever is not along the diagonal there. This product gives me a matrix B, which is given by 33, negative 10, 0, negative 105, negative 32, 0, 105, 30, negative 2. This will be B. And I want you to check my matrix multiplication here to make sure I didn't make a mistake, right? But now we have that the eigenvalues of this matrix, A, and the eigenvalues of B are the same. And look, this is a much easier matrix already, right? When you're taking a determinant, well, you're going to get a lot of zeros popping up here. But we could do this one more step, right? We could also simplify B, or we could find a matrix similar to B by, what would we do next? Let's do negative 3 copies of row 1 or row 2 and add it to row 1, right? So that would be negative 3, 2, B, E, negative 3, 2, inverse, which is the product. Well, this would be 1, negative 3, 0, right? So sorry, I want negative 3 copies of row 1 added to row 2, right? So that would be 0, 1, 0, 0, 0, 1. And then B is the matrix 33, negative 105, 105, 10, negative 32, 30, 0, 0, negative 2. And then times the inverse, right? And the inverse of an elementary matrix is you just flip the sign of the non-zero entry that's not along the diagonal. And again, I want you to verify this product. And what I got here was 3, 0, 15, 10, negative 2, 30, 0, 0, negative 2. And now this matrix C here is similar to B, which is similar to A. And similarity is a transitive property. And so we have that A, B, and C all have the same eigenvalues. So what do we need to do here? Well, then to find the eigenvalues, we could just calculate lambda I minus C, which is going to be lambda minus 3, lambda plus 2, lambda plus 2, and then 0, negative 15, negative 30, negative 10, 0, 0. When we take the determinant of lambda I minus C, that's just going to be, well, lambda minus 3 times lambda plus 2 quantity squared. If you see, you take the determinant, the only term that's not going to vanish is the very first product there, right? It's like lambda minus 3 times the determinant of this. Every other term in that determinant will vanish, which means the eigenvalues of C and B and A, right, which is what we wanted, are lambda 1 equals 3, and then we have a double root of lambda 2 equals negative 2, and lambda 3 equals negative 2. And so this made the computation of the determinant, or of the characteristic polynomial, characteristic equation, much, much easier, right? Because remember, we found the eigenvalues by setting this equal to 0, solving for lambda. And so what you can do, again, is basically realize the steps of converting the matrix A into a row echelon form. If you can realize those steps in terms of elementary matrices, you use that along with the theorem that says similar matrices have the same eigenvalues. Well, then you just go through this process here to simplify to a similar but much simpler matrix C or B or whatever you want to call it. And then you can compute the eigenvalues from there. Okay, so that's all I want to discuss for now in terms of finding and being able to compute eigenvalues and eigenvectors. What we'll do next is we'll look at how to diagonalize a matrix and what a diagonal matrix, what properties does that have in terms of being able to find eigenvalues and eigenvectors.